Yeah, thank you so much, Sasha, for the introduction, and thank you all for coming to listen and for inviting me in the first place. And I'm really sorry, that it's not there in person. It's always so nice to be in DC, but hopefully that changes soon, that we can do those sorts of things again. So today, I'm gonna try to get through a few things. I'm gonna tell you about a new approach to non-smooth optimization. And then from that, once we understand kind of what's going on there, we'll then see that this leads to acceleration for non-smooth optimization, whatever that means, somehow faster algorithms after we get the new approach. And I also briefly mentioned that it leads to faster flow algorithms for a lot of things. And we're really going to spend most of the time up here. I just want to kind of really lay out sort of a lot of the basics of the relevant convex optimization background here so that we understand what's going on, and then just try to get a little bit of a new idea in there. This also means that we shouldn't be in a huge rush. You should really kind of ask questions along the way if something isn't clear. I did end up with a fair amount of formulas on screen occasionally. So, that's always a sign that you have to worry a little bit. And that means, leave some time for questions if it's confusing. So, okay. So as you'll see later though, this non-smooth part maybe should really be called less smooth, because what this work is actually about is kind of the realization that people had spent a lot of energy on things that are very, very smooth in optimization, and a lot of energy on things that are not smooth at all, and that there's something very interesting happening in the space in between that we looked at. So what's optimization? It's this kind of amazing thing that sounds like it's going to be one or two solutions to all of your problems. So you start with some solution domain, D, which we'll think of as a subset of a d-dimensional real space. And then we have a cost function that assigns a cost to every solution. And then we're just asking for an X that minimizes the cost amongst all of the solutions. And then the idea is somehow to start with an initial solution, X0, say, and somehow improve it. And that's really not much of an idea, right? We haven't really said anything yet. Now, we are going to focus on sort of an important subset of optimization, which is convex optimization. That's where you have your cost function. It's this blue thing. And if you draw a tangent line here in one dimension, otherwise it'd be a hyperplane, tangent plane, to the function, then it sits below the function. That's one way of saying it's convex. And the nice thing about this is that you can see if I'm at a point, a locally optimal point, then there'll be a flat tangent line. And then that proves that I'm at a globally optimal point. So that's one of the nice things about convex functions is you can use local optimality to guarantee global optimality. And this also covers a lot of really everything that we know how to do in optimization. A large chunk of it is convex optimization. And also, if a problem is convex, we can generally solve it. Not always, but basically. Okay, then within convex optimization, there are sort of two big areas we should think about. This: how do you deal with smooth functions, and how do you deal with functions that aren't smooth? So let's recap a little bit. How do you deal with smooth functions? So what's a smooth function? It might be something here. I plotted f of x being x squared. It looks like this. A smooth function, the gradient should exist everywhere, and it shouldn't be changing too quickly. Okay, so that to me is a smooth function. We're not going to formalize it much more than that, but you can do different ways of formalizing it. If you have that, then a Taylor series should give you a good approximation of the function. So suppose that you're at some point x, and you want to change it to be at x plus delta, then you can say that the function value is now, we'll do a Taylor series expansion, which says you have based at x, the function value at x plus first derivative times delta plus second derivative at x times delta squared divided by 2 plus a third order term, and so on. And you can try to use this to understand the function value. Now, at your new point, x plus delta. Of course, this is like a multivariate thing, so we actually need to write down derivatives in every coordinate. So the first set of changes we get looks like sum over I, partial derivative in each coordinate, and then times the change in that coordinate. So delta I times the partial derivative at the current point. Second derivatives gives us sum over all pairs, and then times a partial derivative in two coordinates. And then there's something that's a third order term again. And this seems to suggest that if we, let's move ahead. If we make a small delta change, then only the first order term should matter. So if we make the change small enough, we can ignore the second order terms. And then that in turn seems to say, okay, so I want to make this change in the function value negative. I could set every delta I to be the derivative in that coordinate with a minus sign, and then maybe scale it down by some epsilon to make it small. If I make it small enough, then this should be the dominant term and I should make progress. And then just as a bit of notation, we call the vector of all of the partial derivatives the gradient. And so this is called gradient descent. This is that gradient. And so if we recap with that notation, what this says is that we should take our next solution, xk plus 1, to be the current solution xk minus some small epsilon times the gradient at the current point. But also up here, it should be pretty clear that there's lots of other things we could do, right? I was just trying to put something small in this thing, this coordinate, which had at least like maybe the same sign, the opposite sign of the derivative. Now, the function value change that we should get from small epsilon, not so important what it is, but it's just the 2 norms squared of this gradient times this epsilon to make things small, because I got sum of squares of all of these derivatives with a minus sign. Okay, now what makes smooth optimization hard? So the kind of archetypal difficult thing that happens in smooth optimization is that your directions have very different growth rates. So here I've tried as best as sort of my drawing skills allow to draw a function of 2 coordinates, so x and y, f of x, y, this blue thing, and to draw a constant value curve in orange here of function value is 1 and a constant value curve function value is 4. And then I draw the same thing here viewed from above. So that's just the xy plane, and there's the constant value function curve of 1 and 4. And now the trouble is with this elongated shape that we have here, it makes gradient descent do a kind of weird zigzagging, so that you spend most of your time moving back and forth in the steep direction, and you don't make that much progress along the less steep direction. So this zigzagging makes your algorithm slow. Now, it turns out that you can do something that helps quite a lot with this. You can introduce momentum, which then leads to what we call acceleration, which is just a way of saying the algorithm is converging faster. And the idea here is that if there's a direction that I keep moving in across many steps, then I should probably build up some speed in that direction. Like let me add a drift then over time if I keep moving that way. And that's this momentum thing, which indeed does make the algorithms go faster. Okay, so that's one of the main things we can do in smooth optimization land to go faster. There's another thing. So one of the main smooth problems we care about is basically linear equations. So here I'm thinking about doing minimize over x, ax minus b, 2 norms squared. And here we can think of like A being a square matrix, or we can think of it as having like a lot of rows. And I think it's nicer to think about the a lot of rows case, it's more general. This can be an over-constrained problem, then we still have this kind of thing. Okay, and this gives us shapes like this. But now we also know that the problem is a linear equation, it turns out, because it just corresponds to solving the following linear equation: A transpose AX equals A transpose B. Or if the problem is not even over constrained, then it's just AX equals B. Okay, so if we don't have a lot of rows. Okay, but this we can solve directly with Gaussian elimination. Okay, so that gives us a kind of a completely different family of algorithms that gets us the answer. Or more generally, there's sort of descendants of Gaussian elimination. I'll call this direct methods. But it's just we can solve linear equations as a very different way, and this can cope with very, very elongated shapes. And that's nice because not only does it work for linear equations, it also works whenever my problem looks like minimize over x, f of ax equals ax minus b, where f is some nice function. So if gradient descent was going to be fast on just f, then gradient descent plus linear equation solvers will still work for ax minus b on the inside. So if the elongation in the problem, the kind of the weird squeezing of the shape is all coming from a linear map, then I can kind of remove all the trouble that that's causing by solving linear equations. And that's sort of another like important ingredient in smooth optimization. Like a lot of the time, all the hardness of the shape is coming from the fact that there's some linear map that's ill-conditioned. That's what gives this shape, but not always.
So Rasmus, the convergence rate remains the same here as fx?
Yes, but now I pay a price of solving a linear equation every time.
Okay.
So it's like much more expensive to take my steps, but I don't need more steps.
Okay.
Yeah. So that was sort of the two very important things we should know about smooth optimization. So then what is what do I mean when I say non-smooth optimization? But thanks, by the way, that's a good question. So a non-smooth function could be f of x is absolute value of x. So it's like this thing. This is not smooth because there's like a kink in the function here where the gradient changes very suddenly. Another thing could be f of x is the f of x and y, so two coordinates, is the max of x and y. And I tried, I think I will say bravely, to draw that in 3 dimensions here. So we have x and y again, and we have this blue shape. It's my attempt at the planes here of like max x and y. And then we have a constant value curve and another constant value curve. And I drew this scene from above with constant value 1, constant value 4. Okay. So what makes non-smooth optimization hard? So one of the things was the gradient changing suddenly. So if I draw the derivative here with respect to x of f of x, in this function, it goes from -1 and then it jumps to 1 here. So there's like, it's even discontinuous. It's changing very suddenly. There's another problem, which is that we're not getting, in some cases, not getting a lot of information from the gradient, especially in high dimensions. So for example, suppose that my f of x is the maximum over a lot of coordinates. So max over I, x, I, okay, lots of coordinates. Then usually the gradient is non-zero only in that largest coordinate. Like that's the only change I can get in the function is changing the largest coordinate. But that means very little information a lot of the time. Okay, and then you can inherit all the problems that we had in smooth optimization on top of that. So you can still have very elongated shapes and combine them with non-smooth functions. For example, by plugging in a linear map. So like ax minus b, some transformation. Okay, so how do we fix our problems in non-smooth optimization, or at least like approach getting algorithms? So the first standard approach is what's called smoothing. So we can look at like a max of x and y. Here I got a Mathematica plot instead. And we have x, we have y, we have the max of x, y. Then we can replace that with a softmax. So that's this blue curve here. So the softmax of x and y, I'm taking the log of sum of exponentials of the different coordinates. Okay, so this just puts a lot of emphasis on whatever is the largest coordinate. Unfortunately, this gives a kind of trade-off between creating more smoothness and then introducing some error because now you're like dealing with the wrong function. And this trade-off tends to inherently lead to low accuracy algorithms, meaning it works quite well if you're happy to get like a crude solution to your problem, but if you want a very accurate solution, it doesn't really work because either you smooth your function so much that you're never going to find an accurate solution, or you don't smooth it enough and then gradient descent is very slow. So I wrote something precise about this here in some sense, but it's not so important. It's just generally to get to epsilon error, you need something that scales as 1 over epsilon steps. Later, we'll see algorithms that have a much better dependence on epsilon. Okay. And I wrote some math, but that's also not important, just that like max over xi is less than log sum of exponentials. So we can really compare these two things. And then in turn, this is not much bigger. So the most too large by like a log of the dimension. And you can add some constants to get like a less smooth function with an even better approximation, but just scaling things differently. But this has a smoother gradient, but it's not really the right function anymore. So not great. Okay, good if we want low accuracy, but if we want high accuracy, we need something else. And here, there's something else that we're gonna do is called homotopy. This is like basically the approach to high accuracy algorithms in convex optimization. You can think of it as we're gonna do a much weaker smoothing, but then we're not going to just solve one optimization problem. We're going to solve a long sequence of optimization problems that we slowly transform over time so that they have some relationship between each other. Okay, and homotopy is usually in this context understood in terms of hard constraints. So we're going to now look at a function that creates a hard constraint. So here f of x is just a function that's 0 when x is less than 1 and then jumps to infinity. So it's like infinity times an indicator of being, I guess I should have written greater than 1. I think I wrote that wrong in all the remaining slides. Okay. So now we're going to smooth that function, which is a weird function. It's not so important what exactly is the formula. First, we should just notice that it's something that's small and then blows up to infinity as you approach the boundary. And then we can, it turns out some log of 1 over 1 minus x. It's not important. Then we can obviously scale this function differently. And if we scale it by a much smaller constant, it's still going to somehow blow up to infinity at the boundary, but it's going to be smaller everywhere else. So somehow it's going to be a good idea to scale this function by a very small constant. Okay. So now the plan is that we want to solve some, here I wrote like a complete toy minimization problem. We have 2 coordinates. We want them both to be at most 1. And then we want to minimize just the sum of the 2 coordinates with a minus sign, which is like maximize the sum of the 2 coordinates. So that objective here is just saying I want to be as far along the direction of this orange arrow as possible. And the constraints are saying I'm not allowed to be in this blue region. Okay. So now we're going to convert that. We get rid of the constraints, and then we add functions that blow up to infinity at the boundary, 1 for each of these 2 constraints. And then these functions give us these green curves here of constant value. As we get closer and closer to the boundary, there'll be more and more of them. Okay. And we're going to call that whole function fc, where c is like the scaling that we're currently doing in front of the boundary, the barrier that blows up to infinity. Okay, so how does homotopy then work? We have the function for some very large value of c, and by kind of a little trick, we can assume that for very large c, we can find a solution to the problem. So now I have my first solution for a very large c. I'll call it x0 star. It's the optimal solution, but for some very large c, which doesn't give me a lot of information about the real optimization problem. Then I change the constant a little bit in front of the barriers, which changes the optimization problem. So now there's a new optimum. And then I have a different optimum, x1 star. And now, how do I find that x1 star? Well, let's get to it in a little bit. But after I've found x1 star, I'll then change the optimization problem again, get some x2 star, find that one, and just keep doing that many, many times until I get some xt star that's very close to the true optimum x star. Okay. So how do I find each new point xi star? I'll make a local quadratic approximation to my problem. Meeting?
Yes. Do we have time for more questions? I'm not
Oh,
following.
yeah.
I'm not following some of this.
Oh, yeah, we have plenty of time. Let's take a moment.
I'm not following why changing C is changing the minimum. So maybe I did not understand your cost function fully.
Yes. Let's go look here. So it's because, like in the real problem, I just have these two constraints, and then I have this objective, which says that I want to be far out in this direction.
So you're minimizing at xy equal to 1, 1. Is that right?
So my minimum is that x and y both equal to 1. Yeah.
Correct. Okay.
And then I drop the constraints, but I add these functions that blow up to infinity as I approach either of these boundaries, like where I'm not allowed to be.
So I see. Okay.
And then I add a constant, but only in front of the barrier part, not in front of the real objective.
Got it. Thank you.
Okay. I should have included a picture here. We'll get a picture in a second of what these really look like, sort of in Mathematica.
Rasmus,
okay.
How do you know stop when you get to, you say you stop sub t? When you get to true, how do you know when to stop?
Yes, that's a great question. So there's a kind of a couple of different approaches to that. One is that you can usually prove something precise so that you know, like for a certain value of C, I'm very close to the optimum. And then you might just say, okay, I have this proof that I'm close to the optimum. I don't need to be exactly at the optimum. I'm just very close, and then I'm done.
Okay.
Otherwise, if you're actually solving a linear program, you can prove that when you're sufficiently close to the optimum, like very, very close, then there is some kind of rounding trick that gets you to the true optimum. So like if it's linear constraints, then you can like jump to the real optimum once you're close enough to it.
Okay. Thank you.
Oh yeah, but good question. Thank you. So okay, we're gonna find each new point by doing a local quadratic approximation. So we have f of x at some, say, x0 star, the previous optimum, and we want to look at x0 star plus delta. And now this is sort of the new function, right? So I changed the function a little bit. So x0 star is not the optimum anymore. Then I write a Taylor series expansion with like my constant term, my gradient times my update, that's the linear term, and then a quadratic term, which is just, the table, the matrix of all of the pairwise second derivatives, and then some like quadratic function around those. So that's my blue thing here. It's like locally a good approximation. And now we're going to sort of try to compare like the real function, which blows up to infinity at the boundary. And I drew these constant value curves. Remember, the optimum sort of is going to be somewhere here, moves closer and closer to the boundary as I make that constant in front of the things that blow up smaller and smaller. So currently it's here. Now I'm trying to approximate. Oh, by the way, here we get the real picture. So like the barriers blow up to infinity, but then there's that linear part that pushes me that way, and the optimum ends up here. Let's look at this above again. So constant value curves. Now I plug in this quadratic approximation, right? This quadratic function, and it gives me these blue ellipsoids as my constant value curves, just because that's the only thing quadratic functions do, is give you ellipsoids. Now this creates a problem, because that just like, that's a kind of a ball, but the real thing is a square, And squares and balls like are not that similar, especially in high dimension. So if you look at like how close does your constant value curve get to the boundary, and compare a direction where you're only moving towards one constraint versus a direction where you're moving towards many constraints, then the ellipsoid necessarily treats those very, very different. And how big is that difference? It turns out by just thinking about like how well you can fit a ball to a cube in high dimensions, the ratio has to be square root dimension. Between how close it gets in the direction of many constraints versus one constraint. And this ends up kind of governing how many iterations you need. Basically, you need square root dimension iterations precisely because your like ellipsoids don't fit your squares very well. Okay, so how do we actually solve this local quadratic approximation? Well, it's a quadratic function, so it corresponds to some linear equation. So we just solve a linear equation. And that's kind of what we have to do for the local quadratic problem, because it tends to be a very, very elongated, smooth problem. So gradient descent won't work well, but linear equation solving will. And that way we find our update delta, and then we get our new optimum x1 star. Okay. And then we keep doing that all the way up to xt star, and we need xt, we need this t. I think we have another question. Yeah.
Why is the number of iterations the order of square root of dimension? Is it like related to the ratio?
Yeah. I'm not going to really say more precisely about it, but it's really coming from that ratio. It's because like on some level, you always need to use a ball that you know is not going to put you outside of the constraint set. Like, so we're trying to stay inside the constraint set with each update, so that like otherwise things kind of completely break down. But then if the ball is kind of tightly enough fitted that it stays inside the constraint set in the direction of any single constraint, then the ball is far too conservative in the direction of many constraints. It keeps you like way too far away from the boundary. And that gap is square root dimension. And so you need like square root dimension many balls to reach into that direction of many constraints. Okay. But good question, thank you. So that's kind of the level of detail we'll get to, I think. So, okay, we need square root dimension steps roughly to get that xt star is close to x star because of this ratio between the different directions. Like how well does the ball approximate the cube? Okay, and Renegar showed in '86 that using this kind of idea, you can solve linear programs using square root dimension linear equation solves, roughly speaking. Then Nesterov and Nemirovsky showed in '94 that you can actually do almost anything that's convex. So not just linear programs, pretty much any convex problem you can solve this way. But their approach is kind of that you take some convex problem and then you turn it into a bunch of hard constraints, and then you solve that, roughly speaking. And that turns out to be kind of mean that you're inherently stuck at this square root dimension iteration count in some sense. Okay, so square root dimension, you can do anything that's convex, roughly speaking. Now we're going to ask, does it have to be that way for anything that's convex? So we're going to look at things that are less smooth than quadratics, but not completely non-smooth. So think of a non-smooth function with f of x is absolute value of x. It looks like this very pronounced kink here. Now, what about f of x equals x to the 1.1? Still has a pretty big kink. So presumably it's still difficult. That's what we'll try to understand now. And the Nesterov and Nemirovsky result from 94 that we just heard about says you can still do this with square root number of dimension iterations. So things like f of x is the p norm power p of ax minus b. That's like, you should think of maybe, again, A has a lot of rows, M, and X lives in some dimension. And you're trying to, this is an over-constrained problem. You're trying to find the X that minimizes that difference, P norm power P. And you can do this, okay? And you still need square root number of rows, linear equations using homotopy methods, or using at least like the standard homotopy methods. Okay. But now we'll see that we can do a lot better, but it's going to take a very different kind of algorithm. And so we're going to first kind of see like an older, or like an earlier, more well-known instance of this other algorithm. And this is for solving linear equations. So now we're back to a simpler problem, then we'll see that it turns out we can generalize this algorithm a lot. And for linear equations, we have a phenomenon that we call iterative refinement. And it says that if we can solve ax equals b approximately, then we can solve it to high accuracy using the following approach. So first you get some approximate solution x0, okay? Because we said you could solve it approximately. Then you say, okay, how close is x0 to b, which is what I wanted it to be? And you look at the difference, and that's kind of a leftover error. Then you're going to solve a new linear equation to try to deal with that difference. Again, approximately. So now x1 tries to take account of that difference. So your new solution is x0 plus x1. And you subtract that from b, that's your leftover error, b2, and so on. But this is converging very fast, it turns out. So it converges to epsilon error in log 1 over epsilon iterations. Okay, so it's like you get another digit of accuracy for every iteration, which is very powerful. Like you need at most 14 iterations ever. Okay. Now, one way to think about where iterative refinement is coming from is to view the problem as a quadratic function. So we can always think of a linear equation as like a quadratic function being minimized. So think of fx is 2 norms squared of ax minus b. And then think of writing out the Taylor series over here. So there's a constant term, a linear term, a quadratic term. And now what kind of happens is that despite us having error in solving the linear equation, if we at least have the right notion of error, then the errors that we make will sort of correspond to either making this thing a bit too large, this whole number, or a bit too small. And that sort of means that we can view this whole thing as like there's some other functions, one that sits below the true function, sorry, that's the red curve, and one that sits above. And these will be pretty tightly sandwiched. And then when we minimize something that's kind of in between these, it has to necessarily be also making a lot of progress on the original function. So that's one way to carry out this analysis of iterative refinement. So somehow getting an upper bound everywhere and a lower bound everywhere, and being able to relate those to like the changes, like the solution we got is crucial. Okay, so now we're going to try to think about doing the same to p norms. So we have f of x is the p norm power p of ax minus b. And then we write out a Taylor series for it. There's a constant term, a linear term, a term with all the second derivatives, all the way up to pth derivatives. But this becomes kind of too much. So like, let's think about just one coordinate. Okay, and it turns out this really captures all the stuff we need to know. So let's assume that we start in one coordinate with a value of 1. And then we want to make a change in that coordinate of delta. So we want to move to 1 plus delta and get a value of 1 plus delta to the p, where we started with a value of 1 to the p. And then we can write out an expansion of this, which is basically a Taylor series expansion. So, but it's also just the literal exact expansion of like writing out the what's going on here, 1 plus delta. So like a binomial formula, something. Okay, now I can look at all these terms. I can say 1 plus p delta, that's my linear approximation to the function. And then I can look at the second term. It has like a quadratic thing that's going to describe the curvature here at this, like for small delta. And then the last term, delta power p, has to govern the long range behavior of the function. So think of like delta power 4, for example. Then if delta is very large, this is the largest thing. Sorry, this is the largest term. So I made a picture of this. Here, p is equal to 4. And I looked at 1 plus delta power 4 minus its linear approximation. So like all of these other terms. And clearly, if we look out very far, so like very large negative delta or very large positive delta, it has to be governed by the largest power, which is 4. So this has 4th power behavior for long range things. But also just because it's like a function where the Taylor series exists and it's smooth, the derivatives exist everywhere, it has to be locally quadratic, right? So locally it's dominated by this term. And now you just kind of look at this and you say, okay, so maybe this function is actually well approximated everywhere by just a quadratic term to deal with the local stuff and a 4th power to deal with the faraway stuff. Okay. And that's kind of what's going to give us amazing kind of approximations in a little bit. But how do we get these functions that sit above and below? So it turns out that to get a function that sits above, we now take this quadratic behavior and the long range behavior, and we just scale these parts with a factor 2 to the p. Now we have a function that sits above everywhere, the true function. And we can scale it with a factor 2 to the minus p. Now we have a function that sits below everywhere. And these functions globally approximate the true thing. Okay. But so let's compare that to what we did in Homotopy. So in Homotopy, we very much made a local quadratic approximation to a function that was blowing up to infinity. Here we're making a global approximation to like a p-norm function, but with another function that has still a lot of stuff going on. It's not really clear that we made things simpler. Okay. So what does this buy us? This global approximation. It turns out the magic that we get is because we end up being told that if we can do an approximate minimization of linear plus quadratic plus power p, then we can, in fact, make, even if it's a very bad approximate minimizer of this stuff up here, we can still make progress. So because of this sandwiching thing, even a bad solution will make progress. And so the magic trick is really that we have these global approximations, and they're also resistant to only being solved very, very approximately, and they'll still help us make progress on the true function. And what the conclusion is to solve this ax minus b p norm power p, which is what we started with for say p equals 4, you need order 2 to the p log 1 over epsilon iterations. So forget about the 2 to the p for a moment. It's really just log 1 over epsilon iterations. So we again get this super fast convergence. Like 14 iterations is always enough to get essentially an exact solution. It's 10 to the minus 14. And there's like something here that seems weird, maybe, but like, why is an approximate minimization enough? And here, like, this is actually not so surprising at all. It just depends on what am I defining these terms to be. And I exclude the one, okay? So I want to approximately minimize some of the linear term, not the one, just the linear term, the quadratic and the power p. Now, if I approximately minimize that, that's basically saying that I'm capturing like a constant factor of all the progress that I could make by changing delta. You don't need, like, I didn't make it formal enough that you can really prove that to yourself. But basically the idea is that all of these terms account for the progress I could make by changing delta. And I'm gonna, if I can just approximately get that progress, then I like say up to a factor 10, like a huge factor error, then I can still make a lot of progress. And this works at any like level of accuracy that I'll make a lot of progress. So I get these high accuracy algorithms this way. Now there is this factor 2 to the p, which means that I can't take p to be infinity. So I don't get, this would do infinity regression, like p equals infinity, which would in turn solve what's called linear programs, because those turn out to basically be captured by infinity regression. And we don't get there. But for all constant p, this is a very fast approach, it seems. Except I haven't told you how to do an approximate minimization of this stuff yet. But this notion of iterative refinement was introduced by Diksha Adil and I, and Sushant Sachdeva and Richard Peng in a SOTA 2019 paper. So, okay, now we need an approximate minimization of this linear plus quadratic plus power p type function. And we introduce a new multiplicative weight method that does that. And it has something called width reduction, which also leads to this thing called acceleration, which is some kind of faster convergence rate. I'm not going to really explain what is this algorithm. We're not going to go into it. But the key point that I just want to emphasize is that we switch from needing to do something to high accuracy to needing to just do something to low accuracy. And that turns out to be very useful, okay? Because now we can start to ask for all the tools of smoothed approaches, which were able to give us low accuracy solutions to things. So we saw that like when you just need low accuracy solutions, you have a whole bag of tricks that you don't have when you need high accuracy solutions. And so what's kind of going on here is that we can appeal to a lot of the things that people have worked out for sort of getting crude solutions. And then we have this magic tool that is iterative refinement to get a high accuracy solution. Now we solve this problem in numbers. So again, we have this p-norm regression thing with, say, m rows, d dimensions, and the variables. We solve it in m to a constant that depends on p linear equation solves. Now, what does that constant look like? Remember, this would be 1/2 if we were doing Nesterov and Nemirovsky, kind of the old-fashioned methods. Okay, so here I'm plotting that exponent as a function of p, and you can see that it turns out it goes down to 0 at p equals 2, and then at p equals 1, and for very large p, it approaches 1/3. So what this is saying is that like we'll get our regression solution extremely fast as p is close to 2, like very few equation solves. And if p is very large, we might need number of rows in our problem, cube root number of solves, okay? And this should be compared with the square root number of solves that came from the traditional homotopy method. So we're getting cube root dimension instead of square root dimension. And that's, again, the same paper. And I wrote out the formula here, but we don't really care. It's just, you know, goes to 0 at 2, goes to 1/3 for large p. Okay, I should emphasize there's some very important prior work that we are building on. Cristiano, Kellner, Madri, Spielman, and Teng in Stock 2011, they got they got the low accuracy acceleration approach, or at least the beginnings of our low accuracy acceleration that we need in order to get these fast algorithms. And then Bubeck et al. In stock 2018, they developed a completely different homotopy than interior point methods. It's also very unlike our algorithm, but they used that to give an algorithm for p-norm regression that for small p gets also a very small for p close to 2 gets also very few linear equation solves. And it's not really like in retrospect, I think it's probably not a good framework, but it sort of had the grain of the idea that turned into iterative refinement for us. So it's very important background. Okay, now I want to talk a little bit about like what's going on here with this weird curve, because at first it looks like very arbitrary, and then it turns out maybe it's not. So remember, these are like the coefficients that we need in order to solve our like regression problems for different p. Okay, so here, like say at p equals 4, I need something like 0.2. So like this is like a fifth root of number of rows a linear equation solves in order to solve a 4-norm regression problem, something like that. Okay, now Brian Bullins, in a manuscript that I think is not published yet, he made a very nice observation. He showed that you can do 4-norm regression and get our running time again. But he did it by something that's called higher order acceleration, which unfortunately is like, it's a very nice idea that has not worked for anything except this p equals 4. But you can sort of imagine what it ought to look like for all other p, but you just can't quite get an algorithm out of it. What you can do though is you can prove lower bounds. And these lower bounds are not quite in the setting that we're interested in. They're like in a slightly different setting, something to do with low accuracy algorithms. So you need to convert them to high accuracy setting by some heuristics. And it's not clear the lower bound is true anymore. But Brian basically observed that if you convert these lower bounds and you believe his heuristic, then you get exactly our curve for all p. So it might be that these algorithms are optimal for all p in terms of the number of linear equation solves that they get. But it's not clear that you should believe the lower bounds once you've translated them to this setting. Now, the actual formal lower bounds in the low accuracy setting are due to Arjavani et al. In 2018. Okay, and now here's another weird thing. Okay, so Spielman and independently Madri both created a very, let's say, very heuristic lower bound that tries to argue that if you're trying to build a linear program solver using linear equation solvers, you need number of constraints to the 1/3 linear equations. Okay, there are really some gaps in this. They are talking about certain kinds of linear equation solvers only, and like there's a lot of reasons this is a heuristic. But you need at least number of constraints to the 1/3 linear equations. And you should contrast that with the best we actually know for solving linear equations is a coefficient of 1/2. But somehow our thing is 1/3 for any constant p. So I think this leaves some very interesting open questions. One of them being, can you make iterative refinement work for all less smooth functions? So we did it for p-norms, but I think it should be much more general than that. So try to make it work for all less smooth convex functions, not just p-norms. It's really just, you know, like it's this idea that like you look at a Taylor series expansion of your function and you do something about the last term, right? And the other really, really big question is linear programming doable in cube root dimension number of linear equation solves? That's what I think when I look at these curves and these lower bounds, but it's not clear that it is. Okay, so actually now would be a good time for some questions on this. I'll talk very briefly about some other applications of this iterative refinement after, but if there are questions, let's take them now.
Out of curiosity, is the square root dimension algorithms, are they related to Chebyshev polynomials?
That's a good question. I'm gonna say no, actually. I don't think so, because in some sense, the all of these points on our curve are related to acceleration. And acceleration somehow, even though we don't know how to do it yet, acceleration for linear programs seems that it should give this cube root. And so Chebyshev polynomials are extremely related to acceleration. So somehow acceleration in linear programming land, or if it exists, should bring us down to this 1/3. And it seems that we're not leveraging that yet.
So you're saying that, so acceleration in like non-linear programming land and some other simpler context is related to Chebyshev polynomials, but in this more general context, it seems not to be. Is that?
No. I think everything is maybe related. Like all the different acceleration phenomena are related. It's just that this is not the accelerated number here. This 1/2 is not accelerated, but the 1/3 is kind of what is. Yeah.
Okay. And there, so maybe you'll say something about me. I'm vaguely aware that you know, Sidford and others, maybe in TAD, have linear programming algorithms that like roughly run in like matrix multiplication time. How does that compare to getting 1/3 here?
Yeah. These are like kind of incomparable things. So this is really about like the number of linear equations that you solve, whereas they are saying like, if your linear equations are going to be solved by matrix multiplication, well, then you have to pay at least 1 time matrix multiplication. And then it turns out you can fold all the other linear equation solves that you need to do, which for them is still square root n linear equation solves, but you can fold all the costs of all of those later linear equation solves into just be like a little bit extra on top of the first one.
I see. And the techniques you've described wouldn't involve directly solving the linear equations.
Not solving them with matrix multiplication.
Right.
Like at least you don't have to. So in fact, like in this very first paper, this kind of came out in parallel with this first Cohen, Lee, and Song paper that did this. And we also, just because we, I guess, could also get it down below matrix multiplication, even in this setting, using, it turns out to be a bit easier in our setting than it is for linear programs. But to me, the kind of iteration count question is more exciting, because nobody actually wants to solve linear equations with matrix multiplication. Like we would really like to have a fast linear equation solver and then build like these things on top of that.
Right.
And there are some settings where we do. For example, for flows, we have a fast linear equation solver, and then this matrix multiplication time is not relevant anymore. But also, for example, Richard Peng and Vempala, Santosh Vempala had this result last year on getting a fast linear equation solver for sparse matrices. It's not nearly as fast as you would like it to be, but it's faster than matrix multiplication.
Right.
Which is really major. And that also means that now you sort of think, okay, so then actually, if I really want a fast linear equation linear program solver when my linear program is sparse, now I have to use their linear equation solvers. So then I can't rely on matrix multiplication time anymore.
Yeah, that makes sense. Thank you.
Okay, yeah, no problem. Great questions. Okay, so let me rush through, just mention some other results out of this. So you can go a lot further for flow problems, it turns out, with this stuff. It's still a very active area of research. So think about maximum flow. The idea here is that we have a source and a sink, and we want to send as much flow as we can from the source to the sink. I see I'm very low on time, so I think we should finish in 2 minutes, right? So I'll try to keep it very short. So here is like a maximum flow in this graph, just these blue arrows, okay? Now it turns out that maximum flow is a linear program, so you can solve it with homotopy, like all the things we just learned. And something really nice happens. The linear equations that you need to solve are special. They correspond to computing what's called an electrical flow. So these are very special linear equations. And in fact, Spielmann and Teng gave a fast algorithm for those linear equations. Okay, so now you can do your homotopy method surprisingly fast because the linear equations are reasonably cheap. And indeed, like this electrical flow corresponds to solving a linear equation, something Lx equals B. It doesn't matter so much what is it. But the key ingredients for Spielmann and Teng to get a faster algorithm, kind of in retrospect, were the fact that for linear equations, you have iterative refinement and you have Gaussian elimination. And then they combined this with some very nice sampling ideas, and then they got the super fast algorithm. But now we came up with iterative refinement for a nonlinear problem. And then it turns out that, sorry, there's a lot of text here. We can actually do sampling and Gaussian elimination for this nonlinear problem too. And then we get a nearly linear time p-norm minimizing flow algorithm, although at the moment only in unit capacity graphs, which turns out to be like a very, very severe restriction, okay? But this is not using linear equation solvers at all. It's like by repeating all of the theory of linear equation solvers directly for nonlinear problems. And then Lou Sitford and independently Kathuria in Stock 2020 showed how you can build a homotopy on top of our algorithm. So now the local problem that you're solving is not a quadratic anymore. It's a p-norm minimizing flow for a large p. And so now your local problem is like a ball that's much closer in shape to a cube, because like the larger p is, the more your shape kind of fits the cube. That's simplifying a lot of way, but that gives some intuition for why like a local problem that does some large p-norm should be a much better fit. And then they build a much faster homotopy. And this way they get maximum flow in time number of edges of the graph to the 1.33 in unit capacity graphs. And this 1/3, this 1 + 1/3 is in a sense precisely because they figured out how to do acceleration for linear programs, which is what I was talking about before, but only in this very, very special case of unit capacity maximum flow. And then I want to mention that we can remove this unit capacity restriction in a paper that just came out in iCal to get a nearly linear time algorithm for p-norm flow in slightly dense graphs. So not in sparse graphs, but if your graph has like enough density. And like, I think some very, very exciting open questions now is how do you make a nearly linear time p-norm minimizing flow algorithm in all graphs? I think it should be possible. And how do you build maximum flow in all graphs in like this time or something fast, you know, fast enough, whatever you can do in general capacity graphs. And then once you know all that, go back and solve linear programming too. And I think that's all I had planned to say. So thank you so much for listening.
Thanks, Rasmus.
Thank you.
Do we have any more questions? Yeah, it looks like we asked all questions during the talk. Yep. Thanks so much.
Yeah. Thank you. Yep. Let's leave it at that. I have this other Zoom link, right? Yeah. Okay.
Yeah.